So trigonometric identities. So what we mean by an identity first is it's an equation that's always true. I mean, when we solve equations, there's times when you can solve an equation and the solution is all real numbers. That's an identity. It doesn't matter what you plug in, it's going to be true. As opposed to a conditional statement, which is usually when you solve an equation and you get an answer, that's conditional. It's true as provided you plug that number in and that number only. X plus 1 equals 5. That's only true when x equals 4. That's a conditional statement. 2 times x plus 5 equals 2x plus 10. That's always true. I mean, that's the distributive property, right? So that's what we mean by an identity. Statements that are always true. Okay. So, get that out of there. Next. So these are all the different categories of identities. I mean, it's not really important to know these names, but they are what they are. I say that we end up using reciprocal identities, tangent and cotangent identities, and Pythagorean identities a lot. We really don't use too much the last two in this class, but you'll use them in Math and Now quite a lot. One of the concepts that comes up in Math and Now is this concept that they call an even or an odd function. Right? An even function is a function that it doesn't matter if you take for example, if I say the cosine of x equals the cosine of negative x. Because if you look at the graph of the cosine, right, it goes like that, right? It's symmetric with respect to the y-axis. So it doesn't matter if you go a positive distance that way, if you go to the same distance that way, the function value is the same, right? Now, that's an even function. Right? An odd function is like sine. The sine of negative x equals negative the sine of x. So we know what the sine looks like, right? The sine looks like that. So the sine of negative x is the opposite of the sine of x, right? That number is opposite that number. Those are even and odd. That's what these negative angle identities are. But there's more functions, not just trig functions that are even or odd. But that's one of the things you got to look forward to next year. Okay, so let's try some of these. So the reciprocal identities, truthfully, we kind of knew this already, right? When we defined the cosecant, we said it was the flip of the sine. So that's all that's saying right there. Cosecant is 1 over the sine. And the secant is 1 over the cosine. And the cotangent is 1 over the tangent. That's reciprocal identity. Okay, the next are tangent and cotangent identities. Right? I mean, when we were dealing with the unit circle, we said that the sine is the y coordinate, the cosine is the x coordinate, the tangent is the y divided by x. So in a sense, we've really done this one too. Right? Tangent is sine divided by cosine. And the cotangent should be the flip of that. Cosine over sine. Somebody at our door? What does it look like?
Now we need to ask 5 adults about how much they spend on gas weekly.
On gas weekly?
Yeah, do you mind? Down?
Oh my gosh. For one car or 2 cars?
Just write the amount right here.
What is the 2 cars?
Oh, I'll do that later.
Okay. Okay.
Thank you.
Okay, you're welcome. Is this a bad time? Okay, then we get to the Pythagorean identities. Pythagorean identities are like, this is the one you're going to use over and over and over again, right? Pythagorean identities. Now, first thing to understand with this is that when you write sine or cosine or tangent or any of these things with a 2 right there, that's like saying you're squaring the whole thing, right? That's sine 2 theta is sine theta squared. That's just the way you write that, okay? And really that's the way you say it, sine squared theta, right? You don't use say sine theta squared, sine squared theta. So again, when we were using the unit circle, we said that we made a triangle, right? Here's the angle theta. The y-coordinate was there, and that equaled sine. The x-coordinate is there, and that equaled the cosine. And the hypotenuse was always 1 because the radius of the unit circle is 1. So saying that, if you're using the Pythagorean theorem, you say x squared plus y squared equals 1 squared. But we could also say then, because of this, sine squared plus cosine squared equals 1. Right, that's where this comes from. So that's the first one. Again, you should recognize that. When you start seeing things that got sine squared and maybe a 1 in there, like a 1 minus sine squared or a cosine squared minus 1, I mean, in your mind, you got to be thinking, oh, that's some form of this Pythagorean identity. Okay, now if I take, let's say I take this first one here, and I divide both sides by sine squared, right? Sine squared. Sine squared. Actually, I want to do cosine first. It doesn't really matter. So if I divide by cosine squared, both sides, every term. Right, and you can see that by doing that, sine squared over cosine squared, that's the tangent squared. And cosine squared over cosine squared, that's 1. 1 over cosine squared, that's secant squared. So this is just another Pythagorean identity, right? 1 plus tan squared equals secant squared. Again, something that when you see 1 plus tan squared, you got to, if you don't already have it memorized, you should at least say, maybe it's one of those Pythagorean things. Let me turn back to the page where we had that and see if there's some way to like use that to substitute. Okay? And if I do the opposite or not the other, like if I divide each one of these by the sine squared, sine squared, sine squared, sine squared. Again, I'm going to get the 1 is that. This is the cotangent, and that is cosecant squared. So again, that's just another Pythagorean identity. Now, I personally, like, I always remember the sine squared plus cosine squared is 1. I mean, over the years, there's been times when I forget these two, the ones at the bottom. But I know that I got them by just dividing both sides by sine squared or cosine squared. So it takes a few seconds to just, like, do it. Oh, yeah, that's the one. Now, besides just, you know, you're not often going to get something where it's just like there's a 1 plus tan squared and then you're going to substitute secant squared. A lot of times what you get is, for example, maybe you're going to see 1 minus sine squared, right? But if I solve that Pythagorean identity there by subtracting sine squared from both sides, then actually I can see if I get a 1 minus sine squared, I can substitute cosine squared. That's using that same Pythagorean identity. And even sometimes, then you can keep going, right? Because I can say now that this 1 minus sine squared, that's a difference of squares, right? So that's 1 plus sine times 1 minus sine. Sometimes that's a useful substitution to know, right? Same thing over here. I could have, I could subtract 1 from both sides, right? Then I would have tan squared equals secant squared minus 1, right? And there's another difference of squares, right? That would be secant theta plus 1, secant theta minus 1. Okay. And again, I could do the same thing over here, like subtract 1, I would have cotangent squared equals cosecant squared minus 1. So whenever you start to see all these, sine squared, cosine squared, tan squared, I mean, this is where you go to see whether there's something you could do to substitute and simplify. Right, so here's the first kind of problem. Given that sine theta equals 4/5 and theta is in between pi over 2 and pi, find the other values, the values of the other 5 functions. First of all, which quadrant are you in if you're between pi over 2 and pi? In the second quadrant. Remember that pi over 2 is like 90 degrees. And pi is 180 degrees. So you're between 90 and 180, that's the second quadrant. Okay, so remember from the unit circle, in the second quadrant, obviously the sign is positive because it says it's positive 4/5. What about the cosine? Positive or negative? In the second quadrant. That is the x value, right? So you're to the left, that's going to be negative. So, of course, the flips, if the sine is positive, the cosecant is positive. If the cosine is negative, then the secant is negative. What about tangent and cotangent? What are they in the second quadrant? Remember, it's like we said tangent is sine divided by cosine. So that would be a positive divided by a negative, so it's a negative. Okay, so if we have defined, we're going to use these identities to find the other 5 functions. Then the first thing, if you know sine, then the other one you can find is cosine, right? And we're going to use this Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. In the place of the sine, I'm going to put 4/5. So I got 4/5 squared plus cosine squared equals 1. Okay, so this is going to be 16 over 25 plus cosine squared equals 1. So cosine squared equals 1 minus 16 over 25. Cosine squared, then it would be 25 minus 16, 9 over 25. Okay, now you have to solve for cosine, so take the square root of both sides. Right? Now when I do that, I'm going to get cosine of theta equals plus or minus the square root of 9 over 25. Right? But again, we said this is in quadrant 2, so we know that the cosine is actually going to be the negative, not the positive. And we can take the square root of 9 and the square root of 25. This is going to be negative 3/5. Right, the negative again, because you're in quadrant 2 and cosine has to be negative there. Okay, so that was first for the cosine. So now we can do the reciprocals easily enough. The cosecant is 5/4. It's the flip of the sign. The secant is negative 5/3. The tangent should be the sine divided by the cosine. And that will be, the sine was 4/5. The cosine was negative 3/5. So that all simplifies, negative 4/3. And then the cotangent should be the flip of that. So there's all 5. Okay, so try this one. And again, if you get square roots in there, right, you don't want to turn them into decimals, and you got to rationalize denominators. So what quadrant are we operating in? First, so what do you know about the sign, meaning the plus and minus of all these? They're all positive, right? So in the end, it's plus or minus the square root, but we actually only need the positive square root. And we can simplify the square root of 36. So that's the square root of 35 divided by 6. And it's positive. Okay, so then we can go through and do the others. So we have the cosine, so the secant is the flip of that. That would be 6. The cosecant is 6 over the square root of 35, right? But I would have to rationalize the denominator. Right? The tangent should be the sine over the cosine. So the sine was the square root of 35 over 6 divided by 1/6. So that's the square root of 35. And the cotangent should be the flip of that, which will be 1 over the square root of 35, which is the square root of 35 over 35. Okay, so I think I got another U try. So try that one. Which quadrant are we working in this one? Third. Between pi and 3 pi over 2, that's the third quadrant. So what does that tell you about the plus or minus of all these? What is sine? Sine is negative. Cosine is negative. What about tangent? Positive, because sine negative over negative makes positive. Okay. We all should get that far. Right? Now, again, am I going to pick the plus or the minus? In the third quadrant, cosine, which is the x-coordinate, should be negative. So we're going to pick that. Okay, I know I can take the square root of 49 to get 7. How about, can I simplify the square root of 40? How would I break that up? What are the factors of 40 that are perfect squares? About 4 times 10, right? So this is going to be negative 2 times the square root of 10 over 7. Okay, now we can do the others. Okay, the cosecant is negative 7/3. The secant is the flip of that. That's going to be negative 7 over 2 times the square root of 10, which is going to be negative 7 times the square root of 10 over 20. All right, the tangent is the sine of negative 3/7 divided by negative 2 times the square root of 10 over 7, which is negative 3 over negative 2 times the square root of 10. Rationalize, right? And negatives cancel. 3 times the square root of 10 over 20. And cotangent is the flip. But I'm going to flip this here. Not this last thing. I would just have to rationalize the denominator again. I'll just flip this thing. I'll let the negatives cancel, but that'll be 2 times the square root of 10 over 3. So that is that. Okay, next. Simplify. Okay, using those same identities, simplify. Now, when you do this, it's like there's not really like a defined end to it. I mean, sometimes, like when we do this one here, it'll come out to something that's, you know, obviously the end point. But you could get to that place in different ways. Everybody will end up doing these things a little bit different, and it's okay, you know, as long as you still followed the steps properly. I mean, when I grade these tests, it's a challenge on these problems, you know, because some people go, they do that, and the other one goes that, but then eventually, you know, it all comes back around and it's right. So, I mean, it really leaves room for you to be a little creative too, and what you see and how you're going to get there. So if I want to simplify this one using my identities, then, you know, the first thing I noticed in this one here is that there's a cotangent squared. And I know that there's one of our Pythagorean identities that's got that in there. So my first thought is, I wonder if I should do something with that. But then I noticed that one of them's got a cosecant theta, and the other one's got a 1 over sine. Isn't that the same thing? Why don't we make those the same thing? I mean, I'm going to do it like this. I'm going to say this is cosecant theta times cotangent squared theta. And then I'll change that 1 over sine to a cosecant. So now we've got two terms, and they both got a cosecant theta in them, so you factor it out. Cosecant theta, times cotangent squared theta plus 1. All right, but we have an identity that uses that. Right? What does cotangent squared plus 1 equal? Look back a couple slides. It's cosecant squared, right? So actually this whole thing is going to be cosecant theta times cosecant squared theta, which is cosecant to the third theta. And that is as simple as you can get, right? Cosecant to the third. I mean, in first block, I mean, I made the cosecant into 1 over sine, but then at the end I had to like go back and make it back into a cosecant, so that wasn't thinking. I even thought about, again, using the cotangent squared, that would be cosecant squared minus 1. Okay, I mean, there's different ways to get there. Okay, so see if you could figure out how you could simplify that. And I'll give you a hint that sometimes when you can't think of anything else to do, turn everything into the sines and cosines. Like if you got a cosecant, make it 1 over sine. If you got a secant, make it 1 over cosine. If you got a tangent, make it sine over cosine. And then see what happens. You know, usually there's some cancellation involved. So let's see. How could I turn these into sines and cosines? The first sine is going to stay like it is, obviously. How could I turn cotangent into sines and cosines? The tangent and cotangent identity says that's cosine divided by sine, right? That's by definition, basically. Okay, how about the secant? How do you turn that into sines or cosines? 1 over the cosine, right? And now you can see the sine cancels with the sine, and the cosine cancels with the cosine. So the whole thing is 1. Done. Okay. Try that one. So what did this one equal? It's another 1. Do you get that? So if we break it down into sines and cosines, the tangent is sine over cosine. In the numerator, we still got this cosecant is a 1 over sine. In the denominator, we got a 1 over cosine. So the signs cancel here. So now this whole thing is, in the numerator, it's 1 over cosine. In the denominator, it's 1 over cosine, which is 1. So when we say to verify a trig identity, it means to show that, well, however complicated and different it looks on the left side from the right side, that in fact, they are the same thing. By using these fundamental identities, we're going to show that the left side equals the right side. And sometimes you'll make the left side look like the right side. Sometimes you'll make the right side look like the left side. Sometimes you'll change the left side a little bit and then change the right side until it looks like what you just changed the left side to. You know, somewhere in there, though, it's got to end up being that the left side equals the right side. And then when you've done that, then you've confirmed this is going to be true for all values of the variable. Okay, so let's see how that works. Right. Now, usually what they say is that you should start on the most complicated side first. Okay? And that would be, in this case, definitely it's going to be the left-hand side. Okay, let's see. Secant squared theta minus 1. What should that remind you of? generally? One of those Pythagorean identities, right? I mean, there's one of them that says 1 plus tan squared equals secant squared. So if you subtracted the 1 to the other side, actually that would be tan squared. That would be tan squared. So you'd be able to substitute it, right? If I start out with tan squared theta plus 1 equals secant squared, that means that the tan squared equals secant squared minus 1. So I can replace the secant squared minus 1 with tan squared. Okay, now what? Somehow I've got to make that look like sine squared, because that's what the right-hand side is. Anybody have a... Yeah, but let's turn them into sines and cosines and see what happens, right? So the tangent squared would have been sine squared theta over cosine squared theta. Right, but this secant squared in the denominator, right? Secant is 1 over the cosine. So if it's a secant squared in the denominator, that's a cosine squared in the numerator. And now I can cancel cosine squared. And the whole thing equals sine squared. So there you go. That's the right-hand side. We made the left side look like the right side. Right, here's an example of how you could have done this differently. I think at first block I did this instead. I'd say I've got 2 terms in the numerator and 1 term in the denominator. How about if I just split that into 2 terms? What if I say secant squared theta over secant squared theta minus 1 over secant squared theta? Right, that would be 1 minus cosine squared theta. But again, by the sine squared plus cosine squared equals 1, 1 minus cosine squared equals sine squared. So really, a different way, same result. And they're both okay. Okay, verify. Okay. Which side would you think is the more complicated in this one? Yeah, I think the right side probably is the more complicated of the two. And there is a strategy for doing these things that is like this. I'm going to show this in 2 ways, right? Let me copy this. Edit, copy, edit, paste. So if you wanted to work on the right side, and you see that there's a 1 minus sign in the denominator, then what you would do is let's multiply the right-hand side by 1 plus sine x over 1 plus sine x. Okay, notice what happens with that. Okay, in the numerator now I'm going to have, I'm just going to leave it first like this, cosine x. Now I'll distribute cosine x plus sine x cosine x. But 1 minus sine x times 1 plus sine x, that's a factoring of a difference of squares. That's 1 minus sine squared x. So that's a strategy. When you've got a 1 minus a sign, or even a 1 plus a sign, you multiply by essentially the conjugate, and you end up with something like this. Now I can substitute 1 minus sine squared is cosine squared. So I do this. This is cosine x plus sine x cosine x divided by cosine squared x. And now I can split this into two different terms, right? This is going to be cosine x over cosine squared x plus sine x cosine x over cosine squared x. And I can cancel, right? I mean, this cosine will cancel one of those. This cosine will cancel one of those. And what am I left with? This first one is 1 over cosine x, which is secant x. And the second plus sine x over cosine x is tan x. And that's it. That's the left side. I mean, that's a strategy, multiplying by the 1 plus sine x, which you're definitely going to do a lot more of next year. And this year, not so much, but because we said the right-hand side is more complicated. The other thing that sometimes you can do is that if you see you've got two terms, like we've got secant x plus tan x, sometimes by turning them into sines and cosines, you can see that actually you need to do something to make a common denominator or something like that. And that just doing that process will lead you somewhere that simplifies. I mean, in this case, it looks like this. I'm going to make the secant x 1 over cosine. I'm going to make the tan x sine over cosine. And actually, they have the same denominator, so now I can add the numerators. 1 plus sine x over cosine x. Right? And now we've got that whole thing equals cosine x divided by 1 minus sine x. Okay? Now, we don't have the left side equals the right side. But does anybody see what we could do to simplify that? How about cross multiply? Right? If I cross multiply, I'm going to get the 1 plus sine x times 1 minus sine x. That's 1 minus sine squared. And then I'm going to get cosine squared on the other side. So by doing this, I'll get 1 plus sine x times 1 minus sine x equals cosine squared x. And then that is 1 minus sine squared. You know, I could rearrange this. I could add sine squared to the other side, and I would get 1 equals sine squared plus cosine squared. Yeah, I could even take it one more step. 1 equals 1. There you go. I made them meet in the middle. And now I've got 1 equals 1. So in a way, you know, the methods kind of look different, but in the end, at some level, they're really kind of the same. You know, because we ended up still doing the 1 plus sign and the 1 minus sign, you know, and that was kind of the key to getting it simplified or verifying. Okay, so try to verify that one. Again, notice when you see 1 minus sine squared, that should direct you immediately to that page of the Pythagorean identities on it. Okay, what can I substitute for 1 minus sine squared? Cosine squared. That's got to be like the easiest substitution in the world. It should take you less than a second to think, oh, what am I going to do here? 1 minus sine squared is cosine squared. So you go cosecant squared times cosine squared. Okay, but what is cosecant squared? That's 1 over sine squared times cosine squared, right? But that's cosine squared over sine squared equals cotangent squared. And that's what we were asked to show. That's what it is. Okay, I got 2 more. Here's one. Verify. So we've seen something just like this, right? This is a turn into sines and cosines. See what cancels, right? Cosine is the same. Cosecant is 1 over the sine. Tangent is sine over the cosine. And so we cancel. The sine cancels sine. Cosine equals cosine. The whole thing equals 1. So there we go. We just made the left side look like the right side. Okay, one more and then we're done. This is the harder one. Right, so the obvious way to go on this one should be that you look at a tan squared plus 1, and what do you substitute? Secant squared, right? That should be it. Secant squared. And cosine squared minus 1, okay, that's not exactly what you get when you first do that first shuffle of sine squared plus cosine squared equals 1. Usually you get 1 minus cosine squared equals sine squared. So if I flip the order of that and make it cosine squared minus 1, then what does that equal? Negative sine squared, right? So that's negative sine squared. And now we can say secant squared is 1 over cosine, so this is negative sine squared over cosine squared, which is negative tan squared. Now, the other thing is I noticed, I mean, did anybody try to FOIL it? Because if you notice, I mean, it's 2 terms times 2 terms. And if I multiply the tan squared from the left times the minus 1 on the right, I mean, right there I get negative tan squared, which means the other 3 terms must all cancel out. I mean, one way or the other, you know, because it all equals negative tan squared, right? This is how that would have looked. If I just FOILed that, I would have got tan squared, cosine squared, minus tan squared, plus cosine squared, minus 1 equals, well, I don't have to do the equals. I'm just trying to make it look like that. Okay, now this tan squared, that's sine squared over cosine squared. Times cosine squared, right? And I've got a minus tan squared plus cosine squared minus 1. So I can cancel this cosine squared. And now if I put it in order, right, I've got a sine squared from the first term, a cosine squared from over here, minus 1 minus tan squared. Okay, but I know that these 2 together add up to 1. So that's 1 minus 1 minus tan squared, which equals negative tan squared. So either way, you end up getting the same thing. Okay, so again, as I was fixing this before, actually our quiz date is going to be in 531, which is next class, which means you got to go back to the first 2 sections we did. The first one was about graphs of sines and cosines. The second one was about inverse functions. You know, remember how we had to limit the domain and range and all that? What quadrants could you work in? That's 531 through 61. And this one is going to be 6, 6. And homework is that.